All right, howdy everyone. I'm Victoria Schmidt from the T Smart Grid Center, and I'd like to thank you for joining us today for the Smart Grid Center webinar titled GridAgent 1.0 Large Language Model Powered AI Agent for Assisting Power Grid Analysis. If you have any questions during today's presentation, please send them via Q&A feature at any time. We'll do our best to answer any questions as many questions as possible at the end of the presentation. Today's presenter is Chen, who is an assistant professor at the Department of Electrical and Computer Engineering at Texas A&M University, TAMU. He directs the Smart Power Energy and Decision Making Speed Lab and co-directs the consortium on AI and Large Flexible Load, CALL. His research focuses on the integration of control, optimization, and AI for smart power and energy systems. Dr. Chen received his PhD in electrical engineering from Harvard University and his MS in electrical engineering, as well as a dual BS in electrical and economics from Tsinghua University. Before joining Texas A&M University, he was postdoctoral associate with the MIT Energy Initiative at the Massachusetts Institute of Technology. He is a recipient of the IEEE PES Outstanding Doctoral Dissertation Award, the IEEE Transactions on Smart Grid Top 5 Papers, the Best Research Award at the 2023 IEEE PES Grid Edge Conference, and several Best Paper Awards at leading power and control conferences. Dr. Chen, take it away.
Yeah, thank you very much for the introduction. Hey everyone, welcome to the Smart Grid Center webinar. I'm Chen. I'm an assistant professor in the Department of Electrical and Computer Engineering at Texas A&M. So today is my great pleasure to share our very recent work on AI agents for power system analysis and operation. So it's really a very recent work. So if you have any feedback or comments, feel free to reach out, and your comments are very welcome. Before we continue, I'd like to give a quick introduction to my group. My group is called SPEED, and the research of my group lies in the intersection of AI, optimization, and control for smart power and energy systems. Specifically, we are looking at three main research directions, including the coordinated control and optimization of IBRs, dynamic modeling and grid integration of large load, as well as large language model-based agentic AI system for assisting power system analysis and operation. So in today's talk, I will focus on the last topic. So many of you may have the feeling that AI is reshaping the world in many aspects and in many domains, like science, engineering, society, communication, education, and also our daily life. So behind all those AI applications is something called large language model, which is the AI model behind all those applications. For example, the ChatGPT released by OpenAI, Gemini from Google, Llama from Meta. So all those large language models are the foundations of these AI applications. And those large language models, they are not coming from nowhere. Actually, they have been developed for many years. This is a timeline of all the existing large language models. We can see that through, like in the recent decade, there is amazing, remarkable advancements of AI techniques. Especially one landmark is the advent of ChatGPT in 2022. At that time, people were amazed by the remarkable capabilities of ChatGPT. It can think, address complex tasks, and respond in fluent language, just like a human. And AI techniques and large language model is keep advancing and keep evolving. OpenAI has released ChatGPT 4 and ChatGPT 5. Yesterday, Google has released the Gemini 3, which achieves the state-of-the-art performance in many tasks. Since I guess many audience may not in the AI field, may from power energy society, so I'd like to give a brief introduction to large language model. We can even ask this question in ChatGPT. So I have done that. Here is the answer. So if we ask what is large language model, the answer from ChatGPT is a large LLM is a neural network trained on vast test data to predict and generate human-like language by modeling the probability of next word given the prior context. So this answer actually is very professional and very concise. Basically, large language model is a neural network. It's a very large-scale, deep neural network. And in this transformer model architecture, the transformer, this one is not the electrical transformer, is representing the AI neural network model architecture. The paper in 2017 titled "Attention is All You Need" proposed this transformer model architecture. And at that time, nobody knows this paper is going to change the landscape of AI and change the world. Using this transformer model architecture, large language model is doing one thing, that is given the text inputs, it will generate the text outputs, and it answers one question, which is what is the most probable next word that follows this input. So basically, so given a text input, the large language model will make a prediction of the most likely next word after that. And then combining the prediction with the text inputs, keep doing that, then we'll generate the complete answer. Let me give you an example for that. So suppose we enter the inputs, I want to know, and we input this sentence into large language model. So inside large language model, this is the processing process. So first, it will do the embedding. That means it will convert the language, the words, to the numerical numbers so that can be understood, can be processed by the neural network. Then after going through many layers of the attention and the multi-layers neural network, the output is the distribution, is the probability distribution across many candidates next word. For example, here are the candidates: what, how, if, why, about, and they will generate a probability on those candidates. In this example, what, it has the probability of about 43%. How is about 20%. Then the output from large language model could be what. That's the most likely word given the text input. So then the total sentence, the overall sentence will be, I want to know what. Then the large language model will take this sentence as the input, keep going through this process and keep predicting the next word. So in this way, it can generate the complete sentence, a paragraph, or even an article. Okay, so then why do we call this type of AI model as large language model? What does large stand for? It stands for three key features. The first one is large model size. Large language models usually have tens or even hundreds of billions of parameters. So with that large model size, it's capable to handle some very complex queries and tasks. The second large means large training data sets. The large language models are trained on very large and massive corpora, including thousands of books. All the Wikipedia pages, all the web pages, and all the code can be found online. So after training on these large data sets, it can be capable of handling many different tasks and have the general reasoning capability for different topics. The next large means the large compute. To train a very large model through large training data sets, it needs tremendous computations. So that requires hundreds of thousands of GPUs to perform the computation. Because of the large computation, actually, it results in another large, which is a large electricity load. Nowadays, the AI data centers is one of the most pricing and hottest topic in the power industry. So this is the one of the most significant and emerging load in the power industry. So if you are interested, recently we have a review and vision paper on this topic about the electricity demand and grid integration impacts of data centers. If you are interested, feel free to check out this paper. Okay, with these three large model size, large training data sets, and large computes, large language model unlock some new capabilities called emergent capabilities, which we don't observe in the small model. The emergent capabilities include first, the reasoning capability. It can reason, can think, just like a human. The second one is the in-context learning. That means if we give some sample or examples or some demonstrations or some instructions, the model can follow the instruction and to solve some complex problems they don't see before. So with this reasoning and in-context learning capabilities, the large language model can behave like a human expert, which can comprehend very comprehensive questions or queries, and then do multi-step reasoning and find the solution to solve the problem and generate natural language outputs and answers. Okay, so here is a brief introduction about the large language model. Then let's look at what's going on in today's power grid. As we know, power system is a very large-scale interconnected power network with a variety of electric facilities and devices. Itself is very complex. On top of it, now we also have the high renewable penetration. The renewable penetration, especially the solar and wind, is introducing uncertain and fluctuating power into the system, which challenges the reliable system operation. In addition, we are experiencing more frequent and more intense extreme weather events that also challenge the system operation and resiliency. In addition, we also have massive distributed energy resources on the demand side, like EV charging, smart buildings, batteries, solars, as well as the large data center load. All those make the power system operation and control more and more complex. Then the question is, can we leverage the advanced AI tools like large language model to help operate the complex system? Motivated by this question, we try to combine or integrate large language model for power system operation, but it turns out to be non-trivial because of many challenges. So here I like to mention two key challenges. The first challenge is lack of domain knowledge, because large language models are usually trained on some general context, some general corporal. They may not have the expertise in power energy systems. So in some cases, it may have the hallucination. That means the large language model, they don't know the answer, but they can make up stuff confidently. In addition, the practical power grid information is highly confidential. The general public has no access to the confidential power grid information, as well as some domain-specific database. So for example, if we ask ChatGPT, what is the network topology of the Texas transmission system? I guess it cannot generate the right answer because it has no access to the Texas transmission system information. So the second challenge is the professional computation. In power system, the power system analysis requires rigorous, professional, and numerically intense computations. For example, in power flow calculation, optimal power flow, contingency analysis, short circuit analysis, all those analyses require very intense numerical computation. But large language model itself is a language model, which is not good at numerical computation, at least for the current large language models. For example, we can ask large language model to solve the AC power flow for the Texas grid. So even for myself, I don't know how to solve power flow by hand. Then the question is, how can we address those challenges? This is the idea of large language model powered AI agents. So we can use the large language model as the reasoning key components as the brain to think. And then we can integrate the tailored domain-specific database and professional tools to the AI agents. So whenever it needs some professional information, you can first search the domain-specific database and get the relevant information to answer the question. And whenever it needs to do some professional analysis, it can directly use the professional tools to do that. So based on this idea, the AI agents can do more than a single large language model. It can understand natural language. It can interpret and respond just using natural language. And also it can reason and plan. It can analyze the information, analyze the query, and make a plan how to execute how to address the query through doing the sequence of tasks. The last one is it can interact with the environments. It can gather the information from the environments, take actions, and observe the feedback from the environment, and keep evolving to be more and more powerful. So based on this idea, we have developed our GridAgent 1.0, which is a large language model powered AI agent prototype for assisting power system analysis. Our GridAgent has 4 key features. The first one is automation. We can automate professional power grid analysis just using natural language through natural language queries, just like how we use ChatGPT. We can perform power system analysis. Number 2 is the plan and action capabilities. It can intelligently generate and execute task plans to fulfill the queries from users. And also it can use professional tools to do professional power system analysis, like power flow calculation, contingency analysis, OPF solution, short circuit, and topology analysis. So in addition, we have also it can also maintain short-term and long-term memory so that it can remember the historical chats, historical results, and information to ensure the context continuity, and it can retrieve information from the embedded database. Okay, let me show you the architecture of this GridAgent. So here is the overview of the architecture. Given a user query, first we have a large language model-based planner with calibrated prompts. Given the user query, it will make a plan. The plan is a sequence of multiple tasks, multi-step tasks, and for every task is linked to a server. Then the task can be executed in the server and get the results. After finish this sequence of tasks, eventually we can get the outputs and will display to the users. In addition, we have maintained short-term memory. We have a memory variable M0 as the initial memory, and then every time we will concatenate with the outputs and updates the memory and keep doing that. So eventually, in addition to the outputs, final outputs, we also have a memory, which is a summary of all the key information from the historical chats and answers. Specifically, at each server, we use tools to execute the task. And for example, in the server 2, first is MCP based, the model context protocol based server. It has a number of tools embedded in the server and is related to the function of the server. The input to a server is the task, the goal, and the query. Also, we have the current memory as the inputs. Inside a server, so first the server will it will take action to select the tool and run the tool to get the results. We also have a reflection mechanism. The reflection mechanism will think based on the current results if the task has been completed, If not, we'll go back to the action layer and select another tool to continue doing that until it thinks it solved this question. Once the task has been solved, we will summarize the key results based on the question and task and output these results. So this is the overall architecture of the GridAgent 1.0. We can separate into 3 layers, including the planning layer, which make a plan how to complete the query, how to adjust the query. And then the coordination layer is to maintain the short-term memory and to coordinate the execution of each task. Then within every server, we have the action layer, which is ready to select the tools to really finish the task and get outputs. So through this process, with the coordination of these 3 layers, it can adjust some complex user queries in power system analysis. Also, we have embedded some domain-specific documents and a library of several standard Power Grid information into the servers. And for this GridAgent, we have some key innovations. The first key innovation is we call this large language model driven prompt refinement with human feedback. The system prompt is critical in shaping the reasoning behavior of AI agents. It will give the context background and structure the reasoning process and give the formats and guidance how to use the tools and how to generate the formatted outputs. So, but manually crafting the system prompts is labor intensive and can be biased by the human experts' intuition. So in this way, we want to leverage the comprehension and generation capability of large language model to automatically generate the system prompts through a lot of iteration process. And also we have the human experts monitor this process and can directly make some minor edits to change the prompts and change the feedback. So this process goes in this way. For the GridAgents, we have created a library of training queries. For every training query, we have a ground truth results, and then we import this query to the GridAgents, get outputs results. We have a large language model-based judge agents to compare these 2 results and summarize the discrepancy and error. After that, we have the edit agents based on the summarized discrepancy, then to refine the system prompts automatically. In this process, we can also have human experts directly make some minor edits to the discrepancy summary or directly edit the system prompt. So we will refine the prompts after we going through the library of training queries. So for example, here we have a system prompt for the contingency tool use. And we use large language model to generate the initial prompts. Then we give a query test, get outputs. It may not work. We'll output some error information. Then we combine the error information, the prompts with the outputs results and ground truths sent to the judge agents. We'll summarize the results. For the human experts, you can also add some review information. Then all the information is sent to the edit agents to update the prompt. We can have the updated prompt. Then we can send another query, training query for the new prompts, and then get the results, compare with the ground truth, send the error message to the judge agents, do the edits, and then update the prompt. So after going through multiple iterations, we can make sure all the training queries can be successfully executed and get the right information. So this can save a lot of effort from manually crafting the system prompts. So the second key innovation is called adaptive schema-based RAG, retrieval augmented generation. Retrieval augmented generation is a technique used to get the relevant information from some embedded database. So instead of using some general information, you will first search the database to retrieve the relevant information. So this works, the current techniques works pretty well for the text information. But when we look at the power system, because power system, all the data sets, they have some special structure. They usually saved as a table as with many specific features. In this way, the conventional RAG may not work well, especially for the large data sets. So for example, if we ask the question for the Texas 2K system, run the AC power flow and retrieve the top 10 lines with the highest line loading ratio. The conventional RAG is based on the semantic similarity, and it will directly work on the entire table and retrieve the entire table and try to get the relevant information. And in many cases, it cannot get the right answer, especially for the large-scale system. But then our approach is first we have a large language model based selection agent, which is based on the query and the features of the Power Grid database. For example, in this example, you will directly find the relevant table and extract the relevant columns from the table, including the bus name and the loading percentage and the line information. After that, we will rank all those values, because in power system analysis, usually we care about the highest or the lowest values. After doing that, we have a hybrid retrieval based on both the semantic-oriented and precision-oriented retrieval algorithm, and then summarize the results, get the answer. And our approach can work pretty well for the large-scale Power Grid database. So in addition, we want to integrate professional tools to the GridAgent. We use the MCP, Model Context Protocol. MCP is an open source protocol or framework that provides a unified and standardized approach to integrate AI agents with the external database and tools. So we can think of the MCP as an adapter. We can use different tools, different database with different like the formats, input, output information. But MCP can behave like a adapter connecting with different tools and have a unified interface for the AI agents. And based on the MCP technique, we have integrated the Panda Power, which is an open source power system analysis simulator. We integrate Panda Power as to GridAgent. Then we have created 7 servers, including the retrieval server that can retrieve relevant information from documents, from the database, and from the historical information. The power flow server that can solve power flow, for example, AC, DC power flow. OPF server is to run the optimal power flow, gets the optimal generation cost. Contingency, short circuits, topology, they can do the professional corresponding analysis given the power grid information. And also visualization, we can visualize the power network topology and some data sets. Let me give you an example. So for example, we can enter the query for the IEEE 39 bus system. Tell me what are the connected buses for line 11. So based on this query, the GridAgent will first interpret this query and then make a plan. The plan is it can identify this is a retrieval. You can identify the retrieval server to retrieve the relevant information to answer this query. So it will use the retrieval server and to answer this question. First, to initialize the power network, which is the IEEE 39 bus system, and then retrieve the information, save the network, and display the results. So in this case, the from bus is bus 5, and to bus is bus 10. And we can continue asking. So the second query is run AC power flow on the previous system and tell me what's the active reactive power flow of line 12 and total power loss. So the GridAgent will identify this as a power flow problem. So it can use the make a plan to use the power flow server and run power flow to get results, and then outputs the corresponding results, summarize the key answers, and answer the query concisely. Okay, here are the examples for the grid agents, and I also have a demo video I'd like to show to you.
This demo introduces GridAgent 1.0, a large language model-based AI agent prototype for assisting power grid operation and analysis, developed by Dr. Chen's group at Texas A&M. It automates professional power systems.
So this is our user interface.
Natural language requests. GridAgent can load power grid cases, summarize the key features, and visualize the network. Let's take the IEEE 39 bus power system, for example. GridAgent loads the 39 bus system and displays the power network in response to the user's query. It can answer related grid questions by retrieving the corresponding information. For example, what are the connected buses for line 11? What is the shortest path between bus 1 and bus 10? What is the impedance of line 9? What are the voltage limits of bus 3? All answers have been verified as correct against the original grid dataset. Moreover, GridAgent can invoke the right tools for professional power system analysis, such as power flow calculation, contingency analysis, optimal power flow, short circuit calculation, and more. For example, run AC power flow on the 39 bus system and get the active and reactive power flow on line 12 and the total system losses. GridAgent calls the appropriate tool to run a power flow calculation, retrieves the relevant data, computes the total power loss, and displays the result. We can also specify the power flow calculation methods, such as Newton-Raphson, fast decoupled, or run a DC power flow. For example, we can ask GridAgent to run DC power flow and compare the results with the AC power flow method. In response to the user query, GridAgent makes a plan to first run DC power flow, then run the AC power flow calculation, make the comparison, and display the results and difference. GridAgent can also run AC optimal power flow by invoking the OPF tool and get the optimal generation profile and generation cost. Even without professional terminology, GridAgent is intelligent to understand intent and take the right actions by leveraging the powerful reasoning capabilities of LLM. For example, users can just say for IEEE 118 bus system, what if line 117 is cut off? Will it cause any troubles? GridAgent interprets this as a contingency question, selects the right tool to run the N-1 contingency analysis on line 171, and returns the violation results. Moreover, leveraging the LLM's reasoning, GridAgent can plan and execute multi-step tasks. For example, run power flow to find the top 5 lines with the highest line loading ratios, then run N-1 contingencies on those lines and report any operational violations. According to this user query, GridAgent first runs AC power flow to identify the relevant line. Then it invokes the contingency analysis tool on those lines one by one and summarizes the results. GridAgent reveals its full chain of reasoning, planning, analysis, and actions. So the workflow is interpretable and trustworthy. Users can inspect every step to verify correctness. It is also scalable to large-scale power systems. For example, the synthetic Texas 2K grid. We can type the query to load the grid, show the network topology, and run DC OPF as well as all the previous tests on the Texas grid. It displays the solved results of the optimal generation power profiles and the generation cost. GridAgent has demonstrated robust short-term memory capabilities. It recalls prior chats and analysis outputs to support continuous, context-aware conversations. It also maintains long-term memory, retrieving relevant information from large document sets, such as power system operating guides, standards, and regulations. For example, we've embedded the ERCOT planning guide and nodal operating guide in our knowledge base. GridAgent can retrieve relevant information to answer professional questions. For instance, in ERCOT planning, what is LTSA and how is it performed? When should ERCOT post the regional transmission plan? In ERCOT operation stage, at most how many cycles can the under-frequency relay have a delay for load resources? This demo showcases the basic capabilities of our GridAgent 1.0 prototype and underscores the great potential of integrating advanced AI tools for power and energy systems. This demo.
Okay, yeah, that's the demo video, and I'm very excited about this because in this way, as you can see, then for us and for some people, they don't even have the power system background or expertise, but they can still do the professional power system analysis, just typing the question like using ChatGPT. So we are keep improving the grid agents, and we are still working on that. Looking ahead, we have three directions we want to pursue. The first one is we want to enhance the planning and execution workflow so that I can make more reliable plan and text generation for execution. We also want to integrate the feedback and self-evolution capability to the system so that after like multiple queries and round of interaction, you can keep improving and adapt to the user's preference. And also we want to get a human in the loop. So in this process, we can have a human experts to monitor the process and to ensure the outputs and the operation decisions are reliable and safe. The second one is currently the AI agent, the grid agents is mostly focused on the steady state power flow, power system analysis. We also want to integrate more advanced capabilities to the grid agents, including the power system decision making and also the dynamic modeling and the transient analysis capabilities. And the last but not least is we want to explore some practical use cases and really useful applications for the grid agents. So for example, how can we use the grid agents to help the real-time power system operation as an assistant? The other one is, and we use the grid agents to automate the, like for example, the large load generation integration studies, so that in this way we don't need power system experts to run all those tedious power system analysis and studies, but you can just ask grid agent to do all those studies automatically. That can save a lot of effort and time. Okay, so this is the introduction to our GridAgent 1.0, which is a prototype for assisting power system analysis. And we are keep working on this system. And if you have any feedback or comments, feel free to share with us. Okay, I guess the next part is the Q&A. I have seen some questions in the chat window. Let me go through that one by one. The first one is for widespread use and great capabilities, which will critically depend on energy consumption. What are your thoughts on the current efforts on reducing energy needs without sacrificing performance LLM? Yeah, that's a very good question. Right now, because the energy consumption of large model is tremendous. Every day is consuming a lot of electricity and becoming one of the most significant large loads in power system. There are several ways we can reduce the energy needs. So one thing is, do we really need a large model? Can we have some small scale by specializing some tasks? So we don't need a general model for all the tasks. Can we have a smaller, specialized model that has a smaller scale, consume less energy, but can still perform pretty well with the comparable performance with the large model? So I think this is something we can pursue. And I believe in the AI field, in the AI community, they are doing a lot of model improvements, model optimization, algorithm improvements, so that they can reduce the energy need but with maintain the same very similar performance of the large language model. And also in the training and fine tuning process, one way is to integrate the energy metrics into the training performance, so that the training and model development can be energy aware, can take into account the energy use. Okay, the second question is, what if there is a relation for server 1 and server 2 tasks? We have 7 fundamental servers, and then for the user query, we have the planner to decompose the complex query into several tasks to finish that. For example, there is an example like run the AC power flow and then identify the top 5 lines of the highest loading ratio, then run contingency. So it's actually a multi-step task. First, we need to use the power flow server to calculate power flow. Then we will use the retrieval server to retrieve the top 5 lines. After that, we use the contingency server to run the contingency analysis. So that's through the sequence of tasks. Every task is routed to one server for execution. After finish the sequence of tasks, we can get the results. Another question is, I'm currently using optimization methods for black start restoration. I'd like to explore whether a large model-based agent can make decisions similarly to an optimization model. If this is possible, how can it be mathematically defined or represented? I understand how to use LLM in practice, but struggling how to justify the decision-making process mathematically. How can we explore for that? That's a very good question. How can we use the large model for decision-making? This is also one of our direction we want to work on. So for decision-making, so my idea is we don't want to directly use large model to make the decisions, especially for some professional power system decisions. My idea is still use the professional tools, or we write code to make the decisions instead of directly asking LLM to generate the decisions. So similar to the toolbox in the GridAgent, we can add additional tool that is a master in decision making. And every time when we identifies a decision making problem, we can send the task or the query to that server to get the decisions instead of directly ask large language model to generate the decision. I want to ask whether the GridAgent is available for public use. Then we are still developing the GridAgent, so right now it's not open sourced. But we are thinking if we are kind of satisfied with some level of capability for the GridAgents, we may have a public version posted online, so then everyone can use and try and test, and also send feedback to us. Can GridAgent calculate dual variables? Okay, jumping. Dual variables of system constraints, such as I would say yes, because we are using the tool to calculate the OPF. So then the output, including the dual variable, which can be interpreted as the price. Yes, we can get that information. Not open source. What's the advantage of GridAgent to a distribution planning consultant? That's a very good question. That's also one of the motivation we want to develop the GridAgents. We can have a human consultant, but first, GridAgents can do all those analysis and answers automatically, so that everyone can directly use the AI agents through the natural language queries instead of pay a large amount of money to a planning consultant, you can get the same or even better answer from the GridAgents. And you can have any questions, can use the GridAgents at any time for any questions. Is that available for public access? Not yet. How often do you get incorrect answers? How do you prevent against incorrect answers? Yeah, that's a very good question. So here, we have a training process is to refine the prompts. So for that case, we have a library of the training queries. We have make sure all the training queries are one part of the training queries are automatically generates from large language model. We ask the question, ask large language model to generate a number of queries for us. Also, as our system kind of experts, we use our expertise to also generate a number of common questions and test it. So far, at least for some not very complex and questions, if those can be handled by all our servers, it can address all the questions. But we are keep working on that. We want to refine the planning and execution process, and we have some ideas how to make this process more robust and more reliable. Is the GridAgent based on commercial large language model like GPT or open source model? So right now we are using the API. We use the large language model API. Specifically, we are using the GPT-5 API as the large language model. So, but we can also do that downloading some open source model so that we can deploy the system just on in the local computer without using the online APIs. In slide 12, how is the reflex step in MCP server designed? How do we know it's trustworthy, not too strict, or this? Yeah, that's a good question. So right now we are just use the large language model, give the results, give the task. For the task, we have a goal for the task, the goal description, and also some like the ideal results from in the task. So then we use the large language model to judge if the task has been finished or not. But yes, that's a good question. I think it's something we can keep improving. So right now it's directly using the large language model with some prompts to decide if the task has been finished or not. Our grid will have different data formats beyond the standard benchmark case. How can you guarantee the integration of tools will interpret the grid in the right way and make it running? For example, if use on data, will it work with power directly with GridAgents? That's a good question. So right now, our grid data is in the format of power, is in the good format, so we can use the tool directly load the case and run the analysis. But it's also something we need to address. In practical power system analysis, I believe all the data sets are in some specific formats. So if we can adapt the system to the specific formats, I think the system can still work well. How about model fidelity? The majority of utility models are not clean and have a lot of issues. How does the GridAgents resolve this problem? This depending on two things. If it's for the professional tools, it needs some input data or some parameters in the good formats. So at this stage, we still need the model to be well formatted so that it can used by the tools. But later on, we can. So for example, if the data format is not clean, we can have another data pre-processing process using the reasoning and the editing capability of large language model so that it can convert some data sets is not well formatted to the well-behaved, well-formatted data. Or we need some human experts get involved in this process. Is the tool public available? Can we run the tool locally on our laptop? Right now it's not public available, but next time I should prepare a live demonstration. So we have the system in our local computer and it's using GPT-5 API. So if you want to use that tool, you need to get the API access. Also, we are trying to deploy the system in a local computer. So using some open source large language model, for example, the Chen or the Llama, so that we don't need API. We can directly run that locally. But there is some ongoing work. Which large language model does this use? We are using GPT-5, but it's easy to change to other large language model, for example, Gemini and other things, because we directly use the large language model API. Which agentic framework are you using? What if the grid is large with more than 10 nodes? Solving OPF problem will be time consuming. How do you guarantee a timely response from agents? Currently, the framework is kind of like the long graph, but we are not directly using the long graph code. We are doing the coding ourselves to maintain the short-term memory and coordinates the sequence of task execution. But the process is similar to the long graph. If the grid is very large, then we will, because running the OPF, we are using the tools. Yes, the tool will take a long time to solve a very large scale problem, but this is not the focus of our AI agents. This is the focus on the AI tool, the OPF tool. How can we develop more efficient AI tool to OPF tool or with AI help to accelerate the solution process? If we directly use the tool for the very large system, it also takes a lot of time. So we cannot adjust in the GridAgents. This is the focus of the other problem, how to develop efficient OPF solvers. If we have that efficient solver available, we can integrate that into the GridAgents. I have a couple of questions. First, what model is mostly employee, and is there some degree of quantization? We are using the GPT-5 API. Technical queries tend to be harder for retrieval to get important information, as the semantic meanings of the query can diverge from the answer. That's why we want to develop our new retrieval algorithm. The conventional RAG is based on the semantic similarity, so this is not good for retrieving relevant information from power system datasets. Power system datasets has some special structures and features. We want to develop some tailored retrieval algorithm that can specialize in retrieving information from power system datasets. This slide is going to be shared. Yes, I think the slides can be shared. What do you believe are the largest? And we are working on the paper on the GridAgents. So it will be coming out in a few weeks. So feel free to follow up our paper. The paper will have more technical details. How do we construct the GridAgents and how do we do the testing and what's the performance? How would GridAgent tackle dynamic modeling queries? So right now we only have the capability of steady state power system analysis. The GridAgent right now cannot handle dynamic modeling and dynamic simulation problem, but we want to integrate that. So similarly, we can integrate some tools for the dynamic modeling and simulation. So then with those tools, you can run the professional dynamic analysis and modeling. What professional tool? Currently, we are using the open source Panda Power because it's open source and have all those code and data, so it's easy to integrate. But later on, we want to integrate some more professional tools. For example, Power Word you just mentioned. Okay, I get lost in the questions. So there are still many questions, but we are kind of on time. So I'll ask last question. If you have any other questions, feel free to email me. We can discuss more on offline. Suppose I perform ACOPF on the IEEE 39 bus system using one sheet of load. Does GridAgent allow users to input different set of load values or apply other types of input customization, such as modifying generator limits and line limits? Yes, we have the modification capabilities that you send a query to modify, for example, the generator limits, the line limits, add a generator, add a line. Yes, we can do that. How do you know the shortest path in the graph? So that's a very good question. So for the shortest path, initially we just want to ask large language model to answer the shortest path. It can work for very small system, but if the system is pretty large, it fails. So what we do is in Panda Power, it has the topology search functions. We directly use that function to find the shortest path. So it's using the professional tools to do the professional analysis. Okay, there are still many questions, but I think we don't have that much time to finish all the questions. If you want to have any follow-up question, feel free to email me.
Okay, we do have quite a few unanswered questions, but we may be able to answer those later in an email or something like that. We will get back to you on that. Thank you, Dr. Chen, for the insight on the GridAgent 1.0 large language model powered AI agent for assisting power grid analysis. Thank you for the active participation from all participants, and thank you for attending. Please be looking for upcoming webinars and events on the Smart Grid Center website at smartgridcenter.tamu.edu.
Yeah, thank you for participation. Thank you for great questions.
Have a great day.
Okay, bye.